Hi, so my name is Vlad, and I work in Glober's field engineering team. I help customers succeed, debug production problems. And if the pictures don't match, it's not because I had like a face surgery. It's because Vlad broke a leg, and I'm really Avi. So there's something common between us. We both like to tinker with interrupts and device registers and the low-level stuff. So I'll try to do the slides justice. All the credit belongs to Vlad. He prepared this slide deck and did all of the work. So Scylla, one of Scylla's main claims to fame is performance, but sometimes things do get slow, and we want to understand why and fix it. So to do that, we need to understand the root cause. There are many things that can go wrong, and we need to be sure that we have the right one in order to fix it. So there's lots of things that are going on in Scylla at the same time. First of all, Scylla tries to tune everything in the system, from interrupts to NUMA placement, affinity, memory. Everything gets tuned by scripts. And this is mostly automatic, but it can go wrong because it is based on our understanding of current hardware. So if hardware doesn't work exactly as we expect it to, it might go wrong. The disk can become a bottleneck. So if you have a super duper NVMe, maybe you'll have no problem. But if you're using SATA disks, or if you have a disk that's not as fast as it's supposed to be, it might become a bottleneck. You might reach the limit of a node or the entire cluster. The sharded design can introduce its own complexities. There's things like prepared statements, which you're supposed to use in order to gain best performance, but you might not be using it, and you might think you're using it, but you might actually have a bug in your program somewhere that let one statement slip through without being prepared. Hot partitions are a problem in sharded designs, so we'll have to detect them and fix them. Large partitions, so we're continuously improving the support for large partitions, but they're still not handled perfectly, so it's good to be able to detect them. Client load balancing, so Scylla tries to load balance everything, but not all of that is under its control. Some of it is under client control, so we have to find if something went wrong there. Lack of TCP connections, that's related. If you don't have enough TCP connections, there will be bad load balancing. And there can be problems with Scylla is divided into a coordinator role and a replica role. If the coordinator is not balanced, then you will see impact on performance. And you sometimes have too many compactions, and that impacts performance too. All right, so tuning, Scylla tries to take all of the work of tuning upon itself. There's really no reason for everyone to apply the same tuning tips if it can be done by a program, so that's what we did. But that cannot always be perfect, so sometimes it goes wrong. So what Scylla does is takes either of two approaches. One of them is to distribute all of the interrupts evenly between the cores. That is true to the sharded design, where everything is perfectly symmetrical. But that can't be done all the times. Sometimes the network interface cards don't have enough queues, don't have enough interrupts, so they can't be spread along across all of the cores you have in your system. So in this case, what we do is we isolate a core. It's usually the first core in the system. And we assign all of the interrupts to that core, which might sometimes look as two CPUs if you're using hyperthreading. So all of the networking happens on that one core or those two CPUs. And that may become a bottleneck. So if you don't do that, then you might have a bunch of CPUs, not all of the CPUs if you don't have enough queues, and they will have to switch between doing Scylla processing and doing network processing. And because these all happen at the same time, the core will have to switch context between those two operations, and that will hurt latency and reduce performance. So this is why we try to isolate it to a single core. So this is how it looks normally. You have two CPUs, 0 and 8. You can see them at the top that are taking most of the interrupts and most of the CPU in interrupt time, and the rest are doing a lot less work. Usually it's for disk operations, which usually can be perfectly balanced by the hardware and the kernel. So this is how it looks when it works well. So sometimes if it's not working, then what you will see is that you will have CPUs that have a lot of IRQ processing. And the way to fix that is you can reduce the number of queues that the NIC has. So usually it will have 8 or 16 queues, and reduce it to just 2, one for each CPU that handles the interrupt. And this is a command that does it. And we do plan to make this automatic like we did everything else in the future. The disk can also be the bottleneck. So what Scylla does is it splits the disk bandwidth among all of the shards. Each one gets a portion of the bandwidth, each shard tries to drive the disk as much as it can according to the bandwidth that it has allocated. And the way to look to see whether you have a problem with the disk is you can look at the per server disk I/O dashboard. It has a lot of metrics, both on the disk as a whole, and also you can see per shard how each shard is, how much bandwidth and how much IOPS it's accumulating. And you can see with the Linux tools as well, IOStat can tell you how busy the disk is. And another metric that's important is the query I/O delay. So if you see a large delay in processing disk I/O, then you know that you might have a disk bandwidth problem. So this is the per server disk I/O metrics, and you can see on the left is delays. It's split both according to IOPS bandwidth and delay, and also vertically it's split across the various scheduling classes. So there's compaction, query, and commit log. So you can see for each of them how much bandwidth it's consuming from the disk, how much I/O operations it's consuming, and what delay it is incurring as a fact. And if you start to see large delays, then that means that you might have a disk problem. Disk I/O time, this is the same metrics that the IOStat exposes, but in the dashboard. And it tells you what % of the time the disk is busy and the rest of it is idle. It's OK to actually see it at 100% because the disk supports concurrency, so sometimes it can take more. But if it's at 100%, then it's a good indication that there might be a problem and you need to inquire further. So sometimes you have a situation where everything is balanced, all of the shards are consuming the same amount, but still you have the disk is running at a bandwidth that's lower than what's advertised. So one of the problems can be that the I/O scheduler configuration is off. On Amazon, on AWS, we try to preset the values, but on regular systems, on-premise systems, there is IOTune binary that benchmarks the disk and configures it. And sometimes it might be off. Maybe the disk aged, and maybe it did not age very well, so it became slower over time. So perhaps it's off. It's good to check it. You can see the bandwidth and IOPS ratings that IOTune calculated for your disk, and you can see if those numbers make sense. If they don't, it might make sense to run it again and see if you get more reasonable numbers. If not, it's a good idea to look whether there might be a different problem. Perhaps the disk is not configured well. Perhaps you need to run fstrim in order to restore its performance. Sometimes you might run into a problem where you're just reaching the natural limits of the hardware. So if everything is perfectly balanced among the shards and you don't detect, it could be that you're simply overloading the cluster, and the fix for that is to add more nodes. It's also a good idea to keep some spares. Don't run the cluster at close to 100% utilization, because then if you will have a burst, then you will have overload, and that will show itself as huge latencies. So something to keep in mind is that Scylla is sharded. Maybe you heard it like 1,000 times in this conference, but everything in Scylla is partitioned across the CPUs. In the same way that it's partitioned across nodes, every CPU gets ownership of a part of the data. And as soon as you don't balance things perfectly, then one shard is going to be slower than the others. And the general rule is that the cluster runs at the speed of the slowest node, and the slowest node runs at the speed of the slowest CPU. So it's very important to keep things well balanced. So a way to detect it is to look at the main dashboard where you have the CPU utilization or the reactor load and move it from per node setting to per shard setting. So you can see every individual shard, and you can see that in this graph we have a few shards, a few CPUs that are overloaded and others that are underloaded. So it's not balanced and something is wrong there. So we need to drill down and see what the root cause of the problem is. And remember that each Scylla node has two main roles that it takes. One of them is a coordinator, which processes incoming requests from the client driver and selects the replicas that will need to further process it. And the other is a replica. And that role is to actually do the data access and manage the cache and all of that. And the bottleneck can be in either of those two parts. And the first thing we need to do is to find out which role is responsible. So to do that, we look at the coordinator metrics, and we look at the following request. So the first is a request served per shard. If you have some shards that are processing more requests than others, then those shards will be overloaded. So that's the first metric to look at. And you can also look at CQL, and this is practically the same thing, but it is split according to the type of request. So it can be a read request or a write request, and you can get a little bit more information from that. The converse side of that is a replica side. So there is a replica section in the dashboard and the cache section, and that tells you how many requests that node is processing in its role as a replica. So look at those and see whether the dissimilarities, the bad balancing between the shards is in the replica section or the coordinator section. And you can also look at in the I/O section and see if there is imbalance in the I/O operations that the shard is pushing. So here is an example, and here you have a load per shard that is very imbalanced. You have two shards that are way up there in the sky, and everything else is not really consuming CPU. It's not making any progress. And the reason is that those two shards are slowing down the entire node. So what could the reason be? So if you look at the coordinator and look at the request served per shard, then indeed you see that all of the requests are processed on those two shards. So something is clearly wrong. Those two shards are doing the client processing, and the others are not doing anything. And usually the cause for that is that you only have connections to those two shards, or at least active connections to those two shards. And because of that, the other shards don't get to process any requests. And you can look at, to further verify it, you can look at the replica. And here you see that all of the keys are perfectly balanced. All of the replica shards are processing almost exactly the same number of requests per second. So this points the finger directly at the coordinator. The replica is fine. Your key distribution is fine. You don't need to worry about it. But it means that something is wrong on the coordinator side. So usually the connections are implicated in such a case. And it's very easy to verify. You have a metric that tells you the number of TCP connections per shard, and you can look at that, and you can see that you have two shards with a connection, and those are actually three shards, and those are the two shards that are busy, and the rest don't have connections, and therefore they don't get to process any requests. So the fix for that is to make sure that you have enough sufficient connections, tune your driver configuration, and in fact, if you use the just announced Scylla drivers, that problem will not be there at all, because the Scylla drivers automatically generate a connection per shard and make sure to send the request directly to the shards that will process it, so you will not have this problem at all. So that's this problem. Here's a different example. So here again we see a system that is running, and there is some imbalance. You have some shards running at 100% load, and the rest are running below. So the system is not perfectly balanced, and we need to understand why. So we'll look at the request served per shard, and we see that it's not perfectly balanced, but it's also not as bad as it was before. So we don't have a clear indication. The reason for the imbalance could be that the nodes receive fewer requests from the client, but it could also be that there is less spare CPU left over on those shards, on those CPUs, and therefore they're not able to process as many requests per second. So this is not completely conclusive. Now we can switch to the replica, and here we see the number of reads and writes that are processed on a shard. And if we look at the writes first, we see that they are perfectly balanced. All of the CPUs process the same write rate. But if we look at the reads, we see that we have two shards that are processing large amounts of requests per second, and we have all of the rest idle and doing nothing. So when you have something like that, or similar to that, when you have a huge disparity, what's the usual suspect is hot partitions. You have some keys that are receiving all or most of the accesses, and therefore they are very busy. And you have the other, and because there are only, if there are more shards than there are keys, there's no way to get a perfect balance. And of course, sometimes it's not as, it doesn't look exactly like that. Sometimes you have still a small rate at the other shards. This is an extreme example. So we saw that shards 6 and 7 have a huge number of hits, while the others have none. So it's perfectly reasonable to assume that it's a hot partition. Another problem that we have is not using prepared statements. So this is something that all of the tutorials tell you to do, to run a prepared statement. But it's possible that in your code you might have forgotten to to split your code into a prepare phase and an execute phase. And the reason it's recommended is that it allows the database to amortize some of the cost of preparing a query, of parsing the CQL and deciding what to do with it, whether it's a read or a write, and exactly how to perform the query. You can do it exactly one time, and then it's amortized over thousands or millions or billions of requests. And so the overall cost is reduced. So here's an example of how you execute a prepare statement. The first line does a prepare. So it returns you some token that represents the statement on the server side. And then you can repeatedly bind values to the prepare statement. That means that the statement doesn't have to be exactly the same. It can have different keys and different values, and then execute it as many times as you like. So you repeat the bind and execute steps for every query that you want to perform. So how do you know whether you missed preparing a statement? There is a counter for that. There is a prepared statements counter. And every time Scylla does a prepare, it increments a counter. So of course, when the program starts up, it does a prepare. So you will see it incremented a bunch of times. But if you see it continuously incremented, that means that you're not using prepared statements, and Scylla has to compile and parse and compile the query each time you run it. And if that counter is incrementing continuously, you have a problem. So this is a Prometheus Queries that shows you exactly where you have unprepared statements. And this is how it looks like. There is, you can see exactly where it happens. So hot partitions, coming back from the previous example. So you have, because Scylla distributes the token ownership among nodes and among shards, then if you're hitting just one partition, then you will have just one shard that serves that partition. Or perhaps if you have a small number of keys that are being heavily accessed, you will have a small number of shards. Those shards will be very busy. The rest of the cluster will be idle. So again, this is how it looks. You have the replica, you have a few shards with a high response rate, high request rate, and the others are at a much lower rate. So when a specific shard is busy serving requests, it is also not able to serve the iOS well. Recall that we have a single thread doing everything. So if it's doing high request processing, it might not be able to service the disk as much. So it will also underutilize the disk. Also, we partition the disk bandwidth among the shards. So you might not have, a single shard is not able to utilize all of the disk. You really need your workload balanced across the disk in order to make full use of the bandwidth. So how can we nail down the fact that we have a hot partition? And also, we want to know what the key is in order to track the problem further on the client side. So one way to do that is to use SQL tracing. And you can enable a probabilistic tracing, which means that some percentage of the queries, and it's important to select a very small percentage or you will overwhelm the tracing facility, will be traced. And you will see a lot of information about those queries. You will see the keys and the values, and you will see whether those queries hit the disk or are served from cache, and which shard serves those keys. So you can run this set of commands, and it will trace the cluster for 10 seconds. And once you run it, you can look at the results are collected in a special table, in a tracing table, and you can run a select in that table and gather all of the traces for queries that we're running in those 10 seconds. And with a little bit of shell magic, you can isolate the key from that query and run the unique command in order to see how many unique keys were accessed. And if you get a specific, if you get a small number, then you know that you have very hot partitions. We're also preparing a top partitions command that will make this process easier and more automatic. Essentially, it will do the same thing, but it will do it on the server side. So we'll only need to run the top partitions command, and it will collect a list of keys that are being heavily accessed, and it will report those keys to you. So that kind of shell magic will at least be less needed. You will still need to do it in special cases, but in the most common cases, the server will take care of it for you. So here is a query that was running, and you can, if you look at the output of the trace, you can look at the parameters that were sent, and you can see that there are two distinct keys, and you can even trace back in your application what the source of these keys are and punish the offender or fix the problem or whatever. And this is how the trace looks in the trace. So to access a trace, you just execute a normal SQL query on the trace table. And one of the columns is the shard column, which tells you which shard executes a request. And if you follow across many requests, then you will see the pattern that it's just shard 6 and shard 7, which were the ones that were high, executing those requests. All right, so the last typical problem that we're going to cover is huge partitions. So if you have very large partitions, then it will take a long time to process them. And in older versions of Scylla, they were less able to process those partitions without introducing stalls. This is a problem that we're continuously fixing, so it will get less important over time. But still, large partitions do have an impact. And if the data model is not designed to have large partitions, then you might want to detect them and understand where they came from in your application in order to eliminate it. Sometimes it can be due to a bot. For example, if you're tracking users' access to a website, then it might be a bot that is continuously hitting on some URL, and that creates a huge track. and you might want to filter that in your application. So this looks like the influence of large partitions. You have the load rising up, and you have the latency jumping. What happens is that the large partition is consuming a lot of CPU power, and because there is inter-shard communication, every time we need to talk to that shard, it slows down every request, even though it might not be related. So it has a huge impact on the high percentile latencies. Usually the average latencies are not impacted so much. And the way to detect that is you can use a nodetool histograms command, and that generates a histogram of various metrics about the table. And among them, it has the partition size that is generated when during compaction. So it might be a little delayed, but still it's often a good way to see. Also, slow query logging can show you that. There is the output of a CF histograms command, and you can see that here you have a partition that is half a megabyte in size. That's actually not that large, so it could be a lot worse. We've seen partitions that are tens of gigabytes in size and even larger. Another tool that you can use for that is slow query logging, and here is a command for that. I guess we will need to improve that, but right now you can use a REST API to enable slow query logging, and again you can execute a query on the system traces key space, and from that you can see all of the sessions that participated in the slow query, query log, and from that you can select the request size, and you can see the size of the responses that were generated to the queries, and find out, look at which one is the biggest one, and from there you can find out the key, and from there you can trace it to your application. All right, I see that we're running out of time, so perhaps I'll stop, or actually we have just a few more slides. So make sure you understand where the bottleneck is in your application. It can be, look at the CPU load. That's often the first indicator. Switch from node view to shard view. In the node view, everything will be averaged, so you don't get a lot of information. As soon as you see you switch to shard view, then any imbalance issue, you see it very, very easily and very, very clearly. Look at your resources, your I/O, your network, your disk. And when you see an imbalance, remember always that Scylla has those two roles, coordinator role and replica role, and see whether the problem is on the coordinator side, which means closer to your client, so that those are often client problems, or on the replica side, which often deals with key distribution. Take a look at things like background processing. So I see the time is up. So look at the mem table flushes and commit log. Often you can see that on the I/O dashboard, where you can see the delays. So if you see that delays for those components are jumping up, that means that the component is using too much bandwidth, and you might need to increase the resources, increase your cluster size, or improve your disk.